Good afternoon, everyone. Am I audible to you people?
Good
Hello.
afternoon. Yes, you are audible.
Okay. Okay. Thank you. Good afternoon, everyone. Welcome to week sixth of the live session. It's fifth or sixth. I guess it's sixth live session on final element method. I'm your TA Danish Bashir from Structural Engineering Division, Department of Civil Engineering, IIT Madras. So in last couple of the weeks, we were seeing the element equation formulation in last class where I deduced the equation element equation. Yeah, in fifth class we deduced the element equations for a bar element where I told you that element equation for this bar element is given by this E by L matrix 1 minus 1 minus 1 1 U1 U2 U1 and U2 are two nodal displacements uh, QL by 2 QL by 2 plus F1 F2. These are the I mean to say that these are force vectors, these two force vectors. This is the vector of nodal displacements, and this is the stiffness matrix. That is, I told you in the last class, it is written as Ku equals F. That is the basic finite element equation for a bar element. So using these using this formulation only, today we will be solving some numerical problems based on based on this bar equation. So let's start with that. So our problem, actually, it is week six today. So let's start. Problem first. So let's assume we have a bar of this varying cross section like this. It is fixed on one side by this. This is the fixation from one side. It is having one section like this and another section like this. So here you can see that the cross section is varying from 1 to 2. So let's assume that cross section of this element A is equal to 2 centimeter square, and cross section of this element is equal to 1 centimeter square. Okay, and let's assume that so actually I have not made them of equal length. Sorry, let's make them first of equal length. I think this will make them equal length like this and this. Let's assume both sections to be of equal length, each equal to 10 centimeter. Okay, each equal to 10 centimeter. This is 10 centimeter and this is 10 centimeter also. Okay, what else is given in the question? And its Young's modulus E is also given to be equal to 2 into 10 to the power 6 kg per centimeter. I think this unit is wrong there. Should be Newton per meter square or something like that. Let's not go into detail of that. Then what we have to do is that we have to use two elements to solve this problem where it is being acted by a force of by a uniaxial pole, actually a force of this P is equal to P equals 1 kg. Okay, let's say 1 kg is acting. Let's keep the units of this as well, be kg per centimeter. Okay, so what we have to use two elements for this problem. One element will be for this cross section. As the cross section is constant for this thing, we can use one element, like this will be our element 1, and from there the cross section is again varying and it is reducing to 1 centimeter square. We can use another element, we can use second element 2. Okay, and let's label our nodes as well. This will be node 1, this will be node 2, this will be node 3, and this will be element 1 and 2. So moving forward, We will write individually the element equation for each element. So first let me write the general element equation. So taking this element equation, okay, this element equation I will be taking, okay. Moving forward, I will take this one to our this class. So the equation will be, I think it's EA by L, yeah, it is EA upon L. Then we have matrix 1 minus 1 minus 1 1 U1 U2 U1 U2 is equal to QL by 2, where Q is this distributed load, okay. In last formulation we saw what Q was, and F1 F2 are the nodal forces, okay. F1 F2 are the nodal forces that act as on two nodes, okay. Using the same equation we will write the element equation for element first. So let's move to next page. Equation for element first, okay. What will be our equation for element first? It is EA by L. E is given as 2 into 10 to the power 6. Its area of cross section, of this element, area of cross section of this element, okay. It is 2 centimeter square, 2 centimeter square, okay. We will keep the units in 2. It is multiplied by 2. Its length is 10 centimeter, okay. 10, 1 minus 1, 1 minus 1 minus 1, 1, like this. Then U1, U2, U1, U2. It is the nodal displacements of element 1, and U1 is the nodal displacement at node 1 of element 1, and U2 is the displacement, nodal displacement at node 2 of element 1. That's why I'm writing the superscript 1 here, okay, is equal to, if you carefully look at this element like this portion, no, you can see that there is no force acting here, no forcing acting at here, nodal force. So there is zero nodal force here as well, zero nodal force here as well. So I can write it to be equal to 0 comma 0 for element 1. This is equation 1, okay. When I again simplify it, it will come out to be 10 to the power 5 4 minus 4 minus 4 4 u1 u2 u1 u2 of element 1 to be equal to 0 comma 0 0 0 of element 1, okay. Let's name to be this to be equation first, okay. Similarly equation for element second what will be the equation for element second? Writing in the similar fashion, we can write it in that equation 2 to the 10 to the power 6. Its area of cross section. Now what is the area of cross section here? Area of cross section is 1 centimeter square here, okay. We have to write area of cross section to be 1, and its length again is equal to 10, and our matrix will remain same, 1 minus 1 minus 1 1, because it's from the equation. It is now, it's again here nodal displacement of element 2, node 1 of element 2, nodal displacement of node 2 of element 2, okay. That's why so superscript 2 is here. And again we have to see at node, this is element 2, here force F1 is equal to 0, but here F2 is equal to 1 kg, okay. You remember this, okay. So I will be writing F1 to be equal to 0 and F2 to be equal to 1, okay, of element 2. When we will solve this, it will boil down to 10 to the power 5, 2 minus 2, 2 minus 2, minus 2, 2, U1, U2 of 2, U1, U2 of 2 to be equal to 0, 1, 0, 1 of element 2, okay. So let's name this to be equation second, okay. Now we have to assemble these equations, okay. Mm, when we will assemble this, so what we have to do is that this is, so this is element 1, okay. This is element 1. This is element 1's matrix, and this is element 2's matrix. So global assembly will be, global assembly will be so here is a trick for that, assembling these elements. What you people will do is that you will take this matrix here, you will write it here, 4 minus 4, 4 minus 4, 4. This is one matrix, okay? This is of first element, okay? This is first element. For second, you will take this matrix, and it is this matrix, this matrix, and it is this first element should be added to this one, okay? It's last element. So I will show how to write it. We can write it plus here 2, this is only one element, 2 minus 2 minus 2, 2, and this is for second element. How we are able to apply this trick? Because we have numbered the element sequentially like this. These are adjacent elements, and we are numbered them sequentially like 1 node, 2 node, 3 node. Since node 2 is common for element 2 and element 3, that is why 2 element of this is coinciding with 1 element of node 2. That is what here you can see 2 node 2 is coinciding with, this is node 2 of element 1, it is, this is node 1 of element 2. These two are coinciding, okay? These two are overlapping, that's why we are able to write this equation like this. So whatever be the rest of the entries, now we will get a 3 cross 3 matrix. So rest of entries you have to add to be equal to 0. Here it will come out to be 0. This is 1. Then there is one common thing, 10 to the power 5. 10 to the power 5 will come outside. And now here you have to carefully write U1 of global, U2 of global, and U3 of global, okay? U1, U2, U3. That is U1 system, U2 system global, U3, okay? Global values. Then is equal, then you have to uh, assemble the global force vector. Look, this is 0 0. First it will be 0 0. Then this is 0 1. You have to do plus here 0 comma 1. Okay, I will show you. This one is for element 1, this one is for element 2. Okay, when you will perform further steps, we will get an element equation like this. So I can directly write it to be equal to 0 0 1, 0 0 1. Okay, solving it further, we will get a whole global equation to be equal to like this. It is equal to 4 minus 4 0. This is minus 4 6 minus 2. This is 0 minus 2 2. I think this is 2. This is u1 u2 u3, u1 u2 u3 to be equal to 0 0 1, 0 0 1. Okay, so what is the boundary condition now given to be? So we can see that here this side is fixed. So there will be no displacement, like this side is fixed, that is this node is fixed, that is u1 is equal to 0. So our boundary condition is this u1 is equal to 0. When we put this u1 to be equal to 0, what we have to do, it will be 10 to the power 5, again 4 minus 4 0 minus 4 6 minus 2 0 minus 2 2. Now here it is 0 u2 u3, but carefully you are making this side displacement to be 0, but there will come one reaction will come here, okay? So if this side is restraining any displacement here, so any reaction will be coming here, okay? So r, let's take to that to be r1. So we have in force vector we have to replace 0 by r1, 0 and 1. Okay, solving it further. So here is a simple trick. I will teach you what is that trick. That trick is like this. Whenever there is any entry in the this displacement vector to be equal to 0, what you people have to do is that you do one thing. You just cancel that row in the stiffness matrix and cancel that column in the stiffness matrix. Like it is element 1 is 0 here. So this is first row and first column will be 0. Rest you take everything. That is, I'm saying you take this everything you have to take. Okay. So our system will reduce after applying boundary conditions. After boundary conditions, system will reduce to system will reduce to 10 to the power 5. So our matrix will be 6 minus 2 minus 2 2 u2 u3 u2 u3 0 comma 1. Okay, now here you can easily say this is a system of two variables with two equations. You can easily find it, find the solution. The solution for u2 u3 matrix will be u2 u3 vector will be u2 u3 will be equal to 0.25. When you follow this, 10 to the power minus 5, 0.75, 10 to the power minus 5 centimeter. Okay, because everything was in centimeter. So this is our solution for the nodal displacements. We got our nodal displacements. Then the reaction can be computed as, we have to compute this R1, no? We have to compute this R1. So we can take this R1, this system of equation. We have to multiply this row with this vector, that will be equal to R1. So R1 will be given as, so first we will write that equation. That equation will be first to compute R1. Okay. So I told you 10 to the power 5 minus 5 will be common. Then it is 4 times 0 will be 0 plus 4u2 plus 0u3, okay, is equal to R1. Okay. 10 to the power 5. So 10 to the power 5, 4 times u2 is 0.25 into 10 to the power minus 5 equal as R1. So R1 is equal to 1 kg. Look, our equilibrium is also being satisfied. Like 1 kg was being applied from this side, 1 kg is also coming on this side. So system is balanced. So you can check your system solutions like this also. This is a trick. Then we have to compute the strains and stresses in each element. We have the formulas for that. For element 1, strain, strain epsilon 1 will be given as, it is given as 1 by L u2 minus u1. Okay, you can easily compute, putting the values. E1 comes out to be equal to 0.25 10 to the power minus 6 strain, and stress will be then sigma will be E epsilon. Okay, sigma 1 will be E epsilon 1. So when you put E value 2 into 10 power 6 multiplied with the strain 0.25 into 10 power minus 6, you will get a stress of 0.5 kg per centimeter square. Okay. For element 2, you can compute the quantities like the similar way. Strain will be for element 2 will be equal to 1 by L. Now it will be U3 minus U2. Okay. It's clear to you people. It's U3 minus U2. This is node 1 for element 2. This is node 2 for element 2. So it will be U3 minus U2. U3 minus U2. Okay. When we will plug in the values, we will get the value of strain to be 0.5 into 10 power minus 6. Okay, and stress will correspondingly will come out to be stress sigma 2 to be equal to E epsilon 2 equal to 1 into 10, sorry, 1 kg per centimeter square. Okay, so this was the exemplar problem that we solved. Moving forward, now we know how to solve a simple bar problem. If we are given a bar with varying cross section with given boundary conditions and some loads are acting on it, then we can use the bar equation. We can use the bar equation, this equation, to solve for displacements at the ends as well as strains and stresses. Now, what happens in truss? I already told you in the first class. Actually, in truss is actually a special distribution of these bar elements in either in 2D spatial distribution or 3D spatial distribution. So again, we have to solve each and every this bar individually, then combine those bars to form a global system and solve that global system, and we can get the displacement, stress, and strains in each truss member. So the truss is nothing the combination of these bar elements or these bars. So our next topic is analysis of 2D truss. I will briefly uh, take you through the basic formulation of the equations of 2D truss, and then we will solve a numerical problem over this. Okay. And also these PPT notes are being continuously uploaded on that Google Drive. You check these notes there as well, and the lectures are being continuously posted on the YouTube, my YouTube channel that the NPTEL team will be sharing with you regularly. Okay, now what happens in the truss element is that in truss the member can be inclined to any direction. It is not necessary it will be always like this perpendicular or it will be horizontal member. The in truss the members are sometimes like inclined to some angle alpha to the horizontal as well. We will see the formulation equation formulation for the members which is inclined at some angle to the horizontal. Okay, there we have to see the local orientation of that node at that point, and then to transform that local orientation to the global orientation, that is global system of global coordinate system, and formulate the equations. Okay, so for example we have a truss member like this. Sorry. Our truss member is looking like this. Okay, this is our truss member like this. Then what is there? We are having node 1 here for the same member, node 1, and for the another member node 2. Okay, for the other side node 2. Okay, like this. Then we can see that, for example, in its local, it's if we see its local system is inclined like this. Okay, its axis, not local system, its axis is like inclined like this. Okay, its axis is actually axis is like this. So it will be having its own nodal displacements. Let that be equal to d1 here. That's local nodal displacement, and d2 here. Okay, This is its small x axis, okay, xx. But the global system, if we see that actual coordinate axis, it's not like this. Actual coordinates are like, I hope you people are getting my point, okay? This is global coordinate system. That is x comma y, okay? So this is local coordinate system. This is global coordinate system, okay? So what we can do is that this displacement d1, we can take its components in the global coordinate system to be like here it will be u1 along global axis. That first its orientation will be alpha u1 and v1, okay? It will be along y axis u1 v1, and same thing we will do it in this coordinate system at this node, sorry. Let that be u2 v2, okay? Again there will be nodal forces acting on it, okay? So let in, let's make one more diagram. So let us see this. There will be forces acting on this on node 1 in its local coordinate system. So let it the member force be, let it be P1 and P2, okay? This is the member force that is acting. P1 for the internal force, P1 and P2, okay? That can be split into the global coordinates in the components to be F1 acting on x-axis and F1 to be acting along y-axis. Same F2 to be acting along x-axis and F2 to be acting along y-axis. So this is local and global forces. This is local and global displacements. Okay. So we can easily write in the local coordinate system, we can easily write the element equation for this bar element to be equal to, you people know that, EA by L 1 minus 1 minus 1 1. Then we have in local coordinate system, you can see that its nodal displacements are d1 and d2. So we can write d1 d2 to be equal to, what are the nodal forces in local coordinate system? These are p1 and p2. p1 p2, okay? Let's denote it, or we can write it in a matrix form to be k local stiffness local matrix displacements in local to be equal to load vector in local, okay? KLDL RL, okay? You all you people know the meaning of these is Young's modulus, A is area of cross section, L is the length of element, okay? Moving forward, what we can do is that these local coordinates, this uh, you people might have studied this in mechanics that, for example, we have a coordinate system like this, x, y, and then it is being rotated by some angle alpha like this, theta like this, to get x dash, y dash, okay? Same is here. We have x and y, and this coordinate system is rotated by some angle alpha. Alpha here to for a small xy, okay? This is small xy, no? Local coordinate system, okay? So we can write the transformation to be equal to small x y will be equal to the transformation matrix cos alpha, because alpha is the angle of inclination, sine alpha minus sine alpha cos alpha. Okay, cos alpha multiplied by the global coordinates x y. Okay, transformation. After this, where we can see that we have the values like, I forgot to mention here is, for example, this node is at some global coordinates uh, x1 y1, and this node is at some global coordinates x2 y2. We can easily write cos alpha and sin alpha from trigonometric identities. So sin alpha, which equivalently I am writing as s only, okay, to be equal to y2 minus y1 divided by L, and cos alpha equivalently writing as C only, to be equal to x2 minus x1 divided by L. Okay, I hope this is clear to you. And L can be written as the length between these two coordinates. This L. No, this is the length of the bar. L you can easily write. Actually, this L is up to full end of the bar. No, sorry. This is node 2, this thing. This is node 1. We can write L. This is the length of the bar. Okay, this is the length of the bar. By coordinate geometry, L can be written to be equal to x2 minus x1 over whole square plus y2 minus y1 over whole square. Okay, I hope this is clear to you guys. One more thing we can write using this transformation. Using this transformation, relationship between local and local displacements and global displacements. Global displacements can be. We can easily write that relationship between, like the local displacements we have d1, d2. We can easily transform into the global by this transformation matrix. Cos sine 0 0. You have to remember this. This is 0 0 cosine, and the global displacements are u1 v1 u2 v2. Okay, we can equivalently write this to be, or this is d local. Okay, you people know that I already mentioned it. This is d local to be equal to, let's term this to be transformation matrix T. Okay, transformation transformation matrix T, and this is D. This is D, actual D in global system. Okay, so we have one more relation like this. Okay, second. After this, Sorry for the interruption. So D local is equal to T transformation matrix multiplied by the global coordinates. Okay. Now we have initial equation this RL equals DL times KL. Okay. So we have RL equals KL times DL. So DL can be, we can take DL to be this. Okay. So our will be equal to RL will be equal to KL TD. Okay. So what we do is that on the both sides we will multiply by T transpose. Okay. T transpose RL equal to T transpose KL T. Okay. D, like this. Okay. What we did is that T transpose DL, this thing. T transpose KLT, we can replace it by one thing, that is K, and T transpose RL, we can replace it by R, this is D. So our equation will be R will be equal to KD. Okay, this is our equation in global system. Again we are getting the same equation, that is F equals KX. Okay, so where these things are, mm, stiffness matrix in global system is given by, how we can get the stiffness matrix in global system K to be equal to transformation matrix transpose multiplied by local stiffness matrix of the element multiplied by the transformation matrix again. Okay, this thing you can get T. And how you can get the global load vector R. Global load vector R you will get by T transpose multiplied by RL, local load vector. Okay, like this. I hope this thing is clear to you. Where this K, when we will evaluate this K, no, like this K you have to write in this. Let me write it for you people so that you don't have any confusion. Okay, so this K is equal to T transpose. Like T is this, our T transformation matrix is this. We have to take its transpose. Okay, so its transpose is cosine 0 0 0 0 cosine multiplied by local stiffness matrix. Local stiffness matrix is this EA by L, 1 minus 1 minus 1 1. Okay, we will write EA by L multiplied by 1 minus 1 minus 1 1, and this is cosine 0 0 0 0 cosine. Okay, when you will perform this algebra you will get out your stiffness matrix, this matrix multiplication. You will get your this to be equal to EA by L. You will get cos square sine cos minus cos square minus sine cos. Okay, minus sine cos sine square. Okay, sine square. This will be again cos square sine cos sine cos sine square, and this is minus sine cos minus cos square. Okay, this is minus cos square minus sine cos minus sine cos minus sine square, and you, this is your equation for the stiffness matrix in global coordinate system. So the total element equation is, element equation will be, total element equation our will Our total element equation will become like this. We have to take this thing completely. This is stiffness matrix. Copy. We have to paste this. EA by L multiplied by the coordinates U1 V1 U2 V2 to be equal to what is the load vector? F1 in global system. F1 X F1 Y F2 X F2 Y. So for our truss element, uh, which is inclined at some inclination alpha to the horizontal axis, the element equation is this. So we have to write this element equation for each truss element, then combine those element equations in global system, and we can get the finite element global system of equation for our truss. Similarly, same thing we can do here, how we can compute the strains and other things. Okay, we can compute the strains and other things like this. Our strain will be then element strain. Element strain will be given as similarly that epsilon is equal to 1 by L minus 1 1 d1 d2. Okay, okay, and stress, element stress sigma E epsilon, it is given as E by L, it's E by L minus 1 1 d1 d2. Okay, and element axial force, element axial force P is given to be a sigma to be equal to a E epsilon. Okay, I hope you people got these things. Okay, so now let's quickly do one exemplar problem so that you people get to know what we were doing from last half an hour. I will quickly tell you one exemplar problem. So we have one truss element like this. One truss element like this. Another like this. Okay. These are fixed at this point. This is fixed at this side. This is fixed at this side. Okay. And this distance is given to be 300, 300, 300 meter. This is 400 meter. And what else is given? This is inclined to horizontal by an angle theta equals 45 degree, and this is global x coordinate system, this is global y coordinate system, this is global y coordinate system. And what you have to find, and one more thing, this is not 45, sorry, this is theta only, you can easily get the angle. Okay, there is one force P acting here, on this corner. P equals 100 kilonewton at an angle of 45 degree. Okay, so we have to solve this stress problem. We can easily solve this stress problem by taking this to be one element, this to be one element, element 1, and this to be element 2. Okay, and finding the individual element equations, combining those element equations, and then finding the solution. So this will be our element 1, this will be our element 2. Okay, this is our element 1, this is element our 2. Okay, this is like this. This is node 1, this will be our node 2, this will be our node 3. So our global displacements will be like this. Okay, here again it will be like this, as I showed you in the formulation. So it will be u2 v2, it will be u3 v3. Okay, similarly it will be u1 v1. Okay, u1 like from here this side, and v1 from this side, and this is element 1 and element 2. These are global degrees of freedom. Okay, actually this is problem 2. Okay, this is global y. This is problem 2. Quickly we will find its solution. So its solution will be like this. First we will see this L is equal to length of element, this element 1. Okay, this element 1. So element 1 from node 1 to 2. Okay, look, this element 1, this element 1, this, sorry, I have written, uh, I wrote something here and something there. This is element 1. Okay, this is 1, this is 2. So it is from node 1 to node 2. Node 1 to node 2, its L will be simply equal, this is 400, this is 300. Okay, this is 300, this is 400. So this will be 500 from Pythagoras theorem. Okay, L will be simply 500 meter. Okay, and our other things will be L, our cos theta. We have to find this theta. Okay, then its cos theta and sin theta will be, cos theta will be 3 by 5, and sin theta will be 4 by 5. It can, you can easily see it from the figure. So if we write that element equation using the element equation like this element equation, this element equation, its element equation will become, for element 1 will become 1, sorry, this is 151.2, 201.6, this is again 201.6, and this is 268.8. These other things are actually same. So what you have to do, you have to do this thing, you have to transport it to this side with minus sign. Okay, only this is minus 151.2 minus 201.6, similarly minus 201.6 minus 268.8. Okay, other things are like this, and this thing you can write 151.2, 201.6, 201.6, 268.8, and this is symmetric. Remember, the stiffness matrix is always symmetric. U1, U2, U1, V1, U2, V2, and now we have to see the forces as node 1. Add node 1, add node 1, the forces are 100 kilonewton. So the forces along
this. This one component will be like this, and another component will be like this. So x component will be minus 100 kilonewton. This will be 45 cos 45. Okay, another will be sine 45. So this will be minus 100 kilonewton, so 10 power 3 cos 45. Okay, let's not write kilonewton, we will use kilonewton newton. Okay, cos 45. This will be another, its y component will be 100 sine 45. Okay, this will be 0, this will be 0. Similarly for element 2, element 2, when you will write the equation, that is from node 1 to, sorry, node 1 to 3, and you will have cos theta. Since theta is equal to 90 degree, cos theta cos 90 degree is equal to 0, because you can see that this element is inclined at an angle of, this element is inclined at an angle of 90 degree here. Okay, element 2, cos 90 is equal to 0, comma sin 90 is equal to 1. You will get an element equation like this: 0 0 0 0 0 787.5, 0 0 0 minus 787.5, 787.5, 0 0 787.5, and this is symmetric here. Okay, everything is symmetric, and you have to write u1 v1 u2 v2 of element 2. Okay, this was for element 1. Since you can see that at both nodes there are no forces acting, no force is acting here, and no force is acting here. This force is not now acting because we already incorporated this with element 1. This will not be counted twice. Okay, so load vector will be 0 0 0 0. So you have two equations. Simply you have to combine these two equations. Once you will combine these two equations, wait a second, once you will combine these two equations, you will get a global system to be equal to combining, comma global system. Our global system will look like this. It will be a 6 cross 6 matrix. Its elements will be 150, 1.2, 201.6. Okay, 201.6, 105, 6.3. Then this element will be 150, 1.2. This element will be 268.8. This element will be 0. This element will be 787.5. And these elements will be minus 150, 1.2. Then this element will be minus 201.6. And next element will be 0. This will be 0. This will be 0, minus 787.5. Okay, like this. And this will be symmetric from this side. Okay, sorry, I messed up here. Then this will be along, this thing will be along 0 here, and this will be here 201.6. This is along this, and along this it will be 0 again here. This is 201.6. This will be minus 268.8. This will be 0 again here. This will be minus 787.5. This will be 151. This will be 201.6. This will be 0 here again. 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 Okay, later on I will correct this in notes when I will upload. Okay, like this. And we have, this is symmetric system. I'll correct it here only. No need to rush. We can write it to be equal to 201.6, 151.2 minus 201.6, 0, 0. Then this is minus 201.6. This is minus 268.8. This is 0 minus 787. Okay. Then we have 201.6. We have 151.2. This is 201.6. This is 0. This is 0. Then 268.800. Then we have 0 comma 0. Then we have 787.5. These all elements are actually, this is a symmetric matrix. Sorry, this is a symmetric matrix like this. Stiffness matrix is a symmetric matrix. So lower diagonal elements will be just this. You have to replace this. Okay. Now we have u1, u2. We have to write this. We have to write, okay. We will incorporate the boundary conditions as well. So you can see that only this node is free here. That is u1 and v1 are only unknowns. u2, v2, u3, v3 are fixed here. Okay, so it will be equal to 0. So incorporating the boundary condition as well, you will be u1, v1, other all four quantities will be 0. And in place of those four quantities, we will have, first we will have our force minus 70.71. This will be 70.71. This is actually this one, 100 times cos 45, 100 times sin 45. And this will be uh, rx2, ry2, rx3, ry3. Okay, I hope this thing is clear to you guys. So you can see that our four rows are 0 here. So I told you just delete those four rows, corresponding rows and columns like this. Four rows are 0, so you have to delete this row, this row, this row, this row as well. Okay, and delete those columns as well. And we have to delete these columns, last four columns. One, two, three, four. So our system of equations reduces to only this 2 by 2 system given as 151.2, 201.6, 201.6, 1056.3 multiplied by u1 u2. U1 u2 is equal to minus 70.71 plus 70.71. So when you solve this equation, you will get u1 to be equal to 0.7470 mm minus times but u2 to be equal to 0.2095 mm. That is the required displacements and note 1. And you can now compute all the other things, that's the reaction forces as well as local displacements. Okay, I hope this thing was clear to you guys. So in today's lecture, we saw the formulation for a 2D analysis of a truss member. Then we solved one numerical problem where the truss members were aligned like this. So as a homework, you will compute the strains, strains and forces, actual force in members 1 and 2. Okay. So thank you everyone for joining this session. Okay. If you people have any questions, you can ask.
Hello.
Yeah. Hello.
Yeah, this solution is U1 and V1 should be there, no? Not the U1 and U2.
Yeah. Yeah. Sorry. Thank you. Thank you so much. This is U1 and V1. Exactly. U1 and V1. That is global displacement at node 1 and global displacement at along X and Y. U1 and V1. Thank you so much. This is U1 and V1. Thank you for
From
paying attention.
yeah, from this one, no, this when you're calculating the strain, then again we have to transform this to a local coordinate system, no? Or
Exactly.
how it will be?
For getting the strains, because I wrote the strain equations to be in the local coordinate system. So from U1 V1 you have to get D1 and D2. Okay, D1
Okay,
and
okay.
D2, and then you have to use the strain equation, stress equation, and actual force equation. It is similar to the problem that we did it like the here. We have
Yeah,
to,
yeah.
yeah, we did the stress strain here. It's similar to that one only.
And the first example, no, that